Welcome to the 10th pre-recording of the Programming Languages Virtual Meetup. My name is Connor Hoekstra, and in this video we're going to be covering Chapter 3.1. That's the start of Chapter 3 of the Structure and Interpretation of Computer Programs. So up until this point, we've covered Chapter 1 and 2. If you haven't seen those pre-recordings or haven't attended the meetups, check out the full playlist for all of those pre-recordings. But in this video, we're going to be kicking off Chapter 3. So Chapter 3 is entitled Modularity, Objects, and State, and the first section of this chapter is entitled Assignment and Local State. And this first section has three subsections entitled Local State Variables, the benefits of introducing assignment, and the costs of introducing assignment. Chapter 3 starts out by stating the preceding chapters introduce the basic elements from which programs are made. We saw how primitive procedures, which we covered in Chapter 1, and primitive data, which we covered in Chapter 2, are combined to construct compound entities, and we learned that abstraction is vital in helping us to cope with the complexity of large systems. But these tools are not sufficient for designing programs. Effective program synthesis also requires organizational principles that can guide us in formulating the overall design of a program. In particular, we need strategies to help us structure large systems so that they will be modular. That is, so that they can be divided naturally into coherent parts that can be separately developed and maintained. And the text goes on to state that there are primarily two different strategies that we're going to cover in this textbook, the first being the object-based approach and the second being the stream processing approach. So we'll be starting with the object-based approach. The text then goes on to read both the object-based approach and the stream processing approach raise significant linguistic issues in programming. With objects, we must be concerned with how a computational object can change and yet maintain its identity. This will force us to abandon our old substitution model of computation in favor of a more mechanistic but less theoretically tractable environment model of computation. So this is the last thing that we're going to cover, sort of to the introduction to Chapter 3, and at this point we are going to hop into the first subsection of 3.1 entitled Local State Variables. So one of the first things they show us is 4 calls to the withdraw procedure. The first 2 are past 25, the third is past 60, and the fourth is past 15. And you'll note that each of the 4 calls to withdraw, we get a different result, which is completely different to anything we've seen up until this point. So we can infer that the starting balance of the bank account that goes hand in hand with this withdraw procedure is starting at 100. When we withdraw 25, we get 75. We withdraw another 25, we get 50. If we try to withdraw 60 at this point, we'll get the insufficient funds string. And the final call to withdraw, where we pass at 15, we end up with 35. So taking a look at this withdraw function, we can see before we define this, we are defining a sort of global balance to be 100. And then we simply are passing an amount to the withdraw procedure, and we have a simple if expression where we check whether the balance is greater than the amount we want to withdraw, greater than or equal to, and then in the consequent, we have a call to the begin procedure, which we're going to touch on a little bit later, and then a call to set bang, which is this new procedure that this chapter introduces. And this gives us the ability to assign a value to an existing variable. So here we're just basically subtracting the amount from the current balance, and then we have a second expression, which is what the begin procedure allows us to do, is to have multiple expressions that is going to return us the balance amount. If the balance is less than the amount that we're trying to withdraw, we just get the insufficient funds string. So right after this, it basically talks about set bang, which it takes a variable name and a new value for that variable, and we'll do the assignment. So this is an extremely important procedure, and it's going to be very, very crucial for all of what we're going to cover in the next couple chapters. At this point, we're going to read a couple of the footnotes as they were somewhat interesting. The first one is footnote 2 that reads, the value of a set bang expression is implementation dependent. Set bang should be used only for its effect, not for its value. The name set bang reflects a naming convention used in Scheme. Operations that change the values of variables or that change data structures, as we will see in section 3.3, are given names that end with an exclamation point. This is similar to the convention of designating predicates by names that end with a question mark. I really like this. The more interesting part of this, I thought, was the sort of second part, which is talking about how they are denoting modifying procedures with an exclamation mark. I actually referred to this in my algorithm intuition talk, which I'll put, if you haven't seen it, a little link up in the right-hand corner if you want to go watch that afterwards. But at about the 17-minute mark, I talk about how in a podcast, the first time I came across this was someone talking about Ruby and JavaScript and how they use this exclamation mark to mean the same thing. And in C++, you can sort of get similar behavior when you are using algorithms if you use the cBegin and cEnd methods as opposed to the begin and end methods. The C denotes const, meaning that you're not modifying that range that you're using with your algorithm. So I think this is great, giving your reader explicit syntax to know when you have a modifying procedure. The next footnote we are going to look at is footnote number 3, which states we have already used begin implicitly in our programs because in Scheme, the body of a procedure can be a sequence of expressions. Also, the consequent part of each clause in a conditional expression can be a sequence of expressions rather than a single expression. So this is basically just explaining the begin procedure that is introduced here, and it's stating that we need to explicitly use it in if expressions, but we don't need to use it explicitly in the consequence of the clauses in our conditional expression, which makes a lot of sense because I believe in an earlier video I expressed confusion as to why we could have multiple expressions in conditional expression clauses but not in if expressions, and this is basically spelling it out because begin is implicit in the conditional expression. At this point, the text defines a second version of the withdraw procedure, which it calls new withdraw, and at this point it is a higher order function because it's returning a lambda, and instead of globally defining the balance to be 100, it's locally defining it inside the let expression here. And the next footnote goes on to explain this. It says, in programming language jargon, the variable balance is said to be encapsulated within the new withdraw procedure. Encapsulation reflects the general system design principle known as the hiding principle. One can make a system more modular and robust by protecting parts of the system from each other. That is, by providing information access only to those parts of the system that have a need to know. So it's basically saying that if we don't need to put it in global scope, we can put it at a more local scope and increase the encapsulation, which is a good thing to do because if we can limit the amount of pieces in our system that have access to information, it reduces the complexity. At this point, the textbook goes on to define another new version of withdraw called make withdraw, and it's a higher order function as well, returning a lambda with the exact same contents of the if expression that we had before. The only difference here is that we are not defining the balance. We are taking it as a parameter, so we can set what the balance is of our account when we call this procedure initially. We then go on to look at what is going to be the final version of our sort of quote-unquote withdraw procedure. You can see now that withdraw is a procedure within our procedure make account that takes a balance, and this is using message passing, which we looked at the tail end of chapter 2. So you can see here we have 3 internal procedures within make account. We have withdraw, which takes an amount, we have deposit, which takes an amount, and we have dispatch, which is what our make account procedure is going to return. So make account, due to the fact that we are returning a procedure, makes it a higher order procedure. And you can see that the dispatch procedure is just following the message passing pattern that we saw at the end of chapter 2. So it takes a message. If it is the withdraw message, it's going to return the withdraw procedure. If it's the deposit message, it's going to return the deposit procedure. Otherwise, it's going to say, I don't know what you're trying to do because I don't have any procedures corresponding to those messages that you've passed us.
So at this point, we have reached our first exercise, exercise 3.1, which reads, an accumulator is a procedure that is called repeatedly with a single numeric argument and accumulates its arguments into a sum. Each time it is called, it returns the currently accumulated sum. Write a procedure, make accumulator that generates accumulators, each maintaining an independent sum. The input to make accumulator should specify the initial value of the sum. For example, if we define A to be make accumulator passed with an initial value of 5. The first time we pass 10 to it, we should get 15, which is 5 plus 10. And the second time we pass 10 to it, we should get 25. So my solution to this looks as follows. We are requiring rack unit for the unit tests at the very bottom, and then we have a 4-line solution. So we are defining a procedure, make accumulator that takes a single parameter init. On the second line, we are using a let expression to assign sum to have the initial value in it, and then in our lambda that we're going to be returning, so because we're returning a procedure in the form of a lambda, this is a higher order procedure, we are going to have this lambda take a single parameter, and then using our begin procedure, this is going to call two expressions. The first one's going to set sum to be equal to the sum of the current value of sum and the value we passed in, and then we're just going to return the current value of sum at that point. And sure enough, if we do the test that the book has, we define A to be make accumulator with 5. We check what A when past 10 gives us, and that's 15, and then when we do it a second time, we get 25. So pretty straightforward for the first exercise. Exercise 3.2 reads, in software testing applications, it is useful to be able to count the number of times a given procedure is called during the course of a computation. Write a procedure make monitor that takes as input a procedure f that itself takes one input. The result returned by make monitored is a third procedure, say mf, that keeps track of the number of times it has been called by maintaining an internal counter. If the input to mf is a special symbol, how many calls, ? Then mf returns the value of the counter. If the input is a special symbol reset count, then mf returns or resets the counter to 0. For any other input, mf returns the result of calling f on that input and increments the counter. For instance, we would make a monitored version of the square root procedure by defining s to be make monitored square root. Then when we pass it 100, we get 10, and then when we pass it how many calls, we'll get 1 because we've only made one call to it so far. So my solution for this looks as follows. Once again, not too difficult. So this solution only works for a one parameter function f. So you can see here our procedure make monitored takes a single argument, which is our procedure f. Then on the second line, similar to our previous solution, we have a let expression where we are setting count to be 0. Then we have a lambda, so we're going to be returning a procedure from this procedure, once again making it a higher order procedure in the form of a lambda, and this lambda takes a single parameter. So it's either going to be an argument or a symbol, which is why it's called arg or symbol. Then inside the lambda, we have a conditional expression with 3 clauses. The first two deal with when we are getting symbols. So the first one checks if it's a symbol equal to how many calls. If so, it just returns us the count of how many times we have invoked f. If it's not how many calls, we go on to check if it's the symbol reset. I believe the book actually asked us to call this reset count, but c'est la vie. If it's reset, we're setting count back to 0. Otherwise, in the else clause, we have called to set bang to increment our count by 1, and then we are applying the function or procedure f to our argument in this case, because we will know it'll be an argument if we've gotten this far. And at the very bottom, we've got 3 unit tests similar to what we had in the book. So defining s to be a make monitored square root procedure. The first time we make a call to s how many calls, we get 0. Then we call s 100, which gives us 10, the square root of 100. And the second time we make a call to s how many calls, we get 1. So exactly what we would expect. If we move on to the next solution, this is basically the same thing. It looks different only because I've added 3 more unit tests at the bottom here. And this solution deals with multiple argument versions of f. So previously, f could only take a single argument due to the fact that we're just passing 1 here. And this version makes use of the Variadic notation using the dot to sort of split the first parameter from the rest of the parameters. And we just use the head when checking for the symbols. And in the else clause, we just apply f to the cons of head and tails, which is going to use all of the arguments if there are more than one. And so we can see at the bottom here, we just have p similar to s, that is a make monitored version of plus. So we have how many calls before and after, which gives us 0 and 1. And then when we apply 1 and 2 to p, we get 3, which is the sum of 1 and 2. So once again, exactly what we would expect. Moving on to the third exercise, exercise 3.3, it reads, modify the make account procedure so that it creates password protected accounts. That is, make account should take a symbol as an additional argument, as in the following. So you can see here we're taking a symbol, secret password, as our password. And it says the resulting account object should process a request only if it is accompanied by the password with which the account was created, and should otherwise return a complaint. So here, if we provide the correct password, secret password, we're able to withdraw 40, giving us 60. If we give it an incorrect password, then we should get a string that says incorrect password. So here is the original code from the book. Just to refresh your memory, we've got our make account procedure, and then 3 procedures inside it: the withdraw, the deposit, and then a dispatch, which we will be returning from our outer procedure, making this a higher order procedure. The modified version of this to answer exercise 3.3 looks as follows. So I will highlight the different code, which is actually pretty minimal. So we've only got 3 places we need to modify. The first is pretty simple. We just need to add a parameter to make account so that we can take a password as an argument. The second place is that in our dispatch procedure, inner procedure, we need to take a second parameter, which is going to be our input password, which will be checked against the password that's stored in this make account procedure to see if it's correct. And then the last change we need to make is in our conditional expression in our dispatch procedure. We just need to check if the password that was set at the beginning is not equal to the current password being provided, the input password. If it's not equal, then we provide a string incorrect password. Otherwise, everything else is the same. And if you check out these unit tests below, sure enough, when we give the correct password 123 ABC, we're able to do the withdraw and deposits and get the correct amounts. But if we provide a different password, we get the incorrect password string. So although there's a lot of code on the screen, it's only a minimal amount that you actually have to change from what the book gave us. And last but not least, for the first subsection of Chapter 3.1, we are going to look at Exercise 3.4, which reads, modify the make account procedure of Exercise 3.3, which we just saw, by adding another local state variable so that if an account is accessed more than 7 consecutive times with an incorrect password, it invokes the procedure call the cops. So once again, we're just going to be modifying an existing piece of code to answer this solution. So this is the full solution for exercise 3.4, and similar to exercise 3.3, I'm just going to be highlighting the pieces of code that I modified. So once again, it's not that bad. It's only 5 pieces of code. The first thing we're doing at the top is setting a variable fail count in the let expression to be 0. The next 2 things that we're doing is that whenever we have a successful withdraw or deposit call, it means that the password given was correct. So we are just resetting fail count back down to 0, because if there was a number of consecutive calls, this might be at 3 or 4, but we want to set this to 0 anytime there's a successful call, because the program or the question asks us for only for 7 consecutives. The last 2 pieces of code, we'll look at the very last one. It is adding a begin procedure so that we can set fail count to be 1 plus what it was before. So previously we saw just using the +1, but here we're using add 1 just to change things up. And we're still going to return incorrect password at the end of this conditional expression clause. And once we've done this, the last thing we have to do is just add an extra conditional expression clause, which checks, is the fail count greater than 7? If so, return the string call the cops. I know it says invokes the procedure, but it's basically the same thing, and it doesn't stipulate what we should be doing in that call the cops procedure anyways. So yeah, this is basically it. So once again, it looks like there's a lot of code on the screen, but in terms of what we were modifying from our starting point, it's actually not that bad. With this, that concludes the first subsection, which means we're going to be moving on to 3.1.2, the benefits of introducing assignment. So they basically focus, the authors of the textbook focus on 2 different examples. One of them is random, and one of them is Monte Carlo, which utilizes random. And the point that they make is, without assignment, trying to program random procedure is very difficult. And the introduction of assignment makes it much more simple. So if you want, take a look at the text and what they have to say about rand. The more interesting example is the Monte Carlo simulation. The example that they show is this estimation of pi, which you can do by using something called the Cesaro test, which has to do with checking if 2 numbers are coprime or not. And it basically shows 2 pieces of code. The first one is using assignment. You can see here we're using rand, and we don't have to pass any state around to make sure that we're having different seeds from invocation to invocation. And they say that this code is quite easy to understand. And then they show the solution without assignment, and their point is that this is much more hard to reason about. You can see the nesting, it's a lot more nested. We have multiple let expressions at the top, and it's a much more tricky solution. If you look at the bottom and how we're kicking this off, iter trials 0, here we've got iter trials 0 initial x. It's much more difficult to code this Monte Carlo Cesaro example if we don't have assignment. So their point is that in certain applications, assignment drastically simplifies our ability to solve problems, which is great. And with that, we're just going to hop straight into the first exercise from the second subsection. This is a very wordy explanation of exercise 3.5. I'm not going to read through it because I think it's just confusing. I'm just going to explain this in my own words. So I'll read a little bit of it. Basically, the question is asking us to implement a Monte Carlo integration as a procedure estimate integral, which is going to take a predicate and some values x1, x2, y1, and y2 in rectangle for the rectangle, and then an n. So it's just basically asking us to implement a procedure. What is this procedure doing? It is going to be used to estimate the value of pi once again. So this question is basically saying, say we're given x1, x2, and y1 and y2 that define the corners of a square or a rectangle, and then you can have a circle inscribed in that square. And the point is here is that if we were to take sample random points, so generate a random value between the x1 and x2, and then a random value between the y1 and the y2, we're going to get a point that lies somewhere in this square. And if we use a predicate, which is what they mentioned as p, which we can get from rearranging this function here, or I guess this is the predicate function. So if we plug in x and y into this function and it's less than 3 squared, we know that it lies within our circle. Otherwise, it's going to be in this red area. And if we take the proportion of points that lie in this circle over the total number of points that we generated that lie in this square, we're able to get a fraction of the area of just this circle to the area of the whole square. And because we know what the area of the square is, then we can get an approximation for the area of the circle and then back out pi. So it's a pretty interesting problem. I've heard that this comes up in interview questions sometimes. How can you estimate the value of pi? And this is typically the answer that is given. So it's an interesting problem. Let's go ahead and take a look at the solution. Note that I did not make use of the Monte Carlo integration procedure that they gave us earlier. I just sort of coded this from scratch using threading. And note that they gave us this random in range procedure to give us a random value between the x values that were given, x1, x2, and y1 and y2. I've modified it a bit to make sure that I get a decimal value because I did not want to deal with integers because you end up with a rougher estimate of pi. But once you have this, you basically just define your procedure estimate interval. It takes p, which is a predicate, your 4 values for the corners of the square, and then n, which is the number of samples you're going to, or the number of points you're going to sample in order to generate your estimate for pi. So the higher this is, the more accurate your value of pi will be. And then inside your procedure, we've got 2 things in our let expression here. The first one is just the area of the rectangle. So that's just the multiplication of the length of your x times the length of your y's, or the delta between your x's and your y's. Note that if this was a rectangle and you had an ellipsis, this wouldn't be equal, but in this case, we know that the difference between our x's and y's are the same. And then we are basically setting random point to be a procedure that generates a random point. So we're calling random in range twice, once with the x1 and x2 values and once with the y1 and y2 values. So now we have a nice procedure to generate us a point xy in our square. Once we have this, we kick off our threading by making a call to generate n random points. So this is going to give us a list of the n xy points. Then we're going to map each of these points to either a 1 or a 0. It's a 1 if it falls in our circle. So we're just applying our predicate p to our point, our lowercase p, and if this is true, well, we're giving it a value of 1 because it falls in our circle, otherwise 0. Then we're summing all these up, and then we're dividing it by n and multiplying it by the area of our rectangle, which is going to give us an approximation for the area of the circle. And once we have that, we just basically need to test it out. So we pass it the predicate function that was given in the question, and then the values 2, 8, 4, 10, which are the corners of the square that we were given, and then just a value for n. So here I'm using 100,000. And if you do this, you get an approximate value for the circle of 28.18. And then when you divide this by the radius squared, which is 3 squared, which is 9, you can back out your estimate for pi, which here is 3.14144, which is pretty close to pi, which is 3.14159. So pretty interesting question. I know it's a bit wordy, but if you can get through it, it's worth solving. And this takes us to the last subsection of 3.1, entitled The Costs of Introducing Assignments. So the textbook states programming without any use of assignments, as we did throughout the first 2 chapters of this book, is accordingly known as functional programming. So if you watched the first pre-recording or were at the meetup of the Programming Languages virtual meetup, the first one, I mentioned that Robert C. Martin, on the first episode of the Functional Geekery podcasts, he is a big fan of this book, and one of the things he points out in that podcast is that you get to the 3rd chapter, and they point out that at no point in the first 2 chapters did we use assignment, and he thought that this was mind-blowing, so he went back and checked, and sure enough, we hadn't used any assignment. So it's a pretty big deal that up until this point, everything we've done without assignment, and so they're pointing out that when you're not using assignment, this is known as functional programming. And it goes on to explain how when you have procedures, when given the same arguments, so here it's showing W20 and W10, which gives you 5 and -5. But if you made a call to W20 a second time, you'd end up with -15. And so there's multiple points they make about why it's confusing, but one of the biggest ones is that you don't end up with the same result when you pass procedures the same value. And that makes it much harder. It makes it much harder to reason about your programs, which basically the text explicitly states. So it goes on to say, a language that supports the concept that equals can be substituted for equals in an expression without changing the value of the expression is said to be referentially transparent. Referential transparency is violated when we include setbang in our computer language. This makes it tricky to determine when we can simplify expressions by substituting equivalent expressions. Consequently, reasoning about programs that use assignment becomes drastically more difficult. So the author's pointing out that in our functional programming model, it's much more easy to reason about what our programs are doing because we can be certain of substituting one expression in for another because we don't need to worry about local state or the environment model. We know input X is going to give us the results of inputting X into a procedure will always give us the same result. The text then goes on to state, in contrast to functional programming, programming that makes extensive use of assignment is known as imperative programming. And I believe the next slide is a footnote. So in the text, they're remarking basically and advocating for this functional programming style as being easier and sort of a better place to start from. And then they have this footnote. In view of this, the fact that functional programming is a better place to start than imperative programming, it is ironic that introductory programming is most often taught in a highly imperative style. This may be a vestige of a belief common throughout the 1960s and 70s that programs that call procedures must inherently be less efficient than programs that perform assignments. Steele 1977 debunks this argument. Alternatively, it may reflect a view that step-by-step assignment is easier for beginners to visualize than procedure call. Whatever the reason, it often saddles beginning programmers with, should I set this variable before or after that one, concerns that can complicate programming and obscure the important ideas. So a very interesting footnote. The author's basically stating that it's sad that most, CS 101 intro courses at different post-secondary institutions focus on imperative languages. And sure enough, in my my 2 introductory CS courses in university, I learned Python in my first one and Java in my second one, which are both imperative languages, and didn't learn functional programming until like 5 years into my professional career. So yes, very sad that CS 101 courses focus on imperative programming languages. Interesting, though, that this course was taught at MIT and also the Berkeley 61A course that we're looking at. Both of these use the MIT or the SICPig book and focus on scheme, which is good to know that some universities out there are focusing on all of these paradigms and including functional. The text then goes on to state, the complexity of imperative programs becomes even worse if we consider applications in which several processes execute concurrently. We will return to this section in 3.44. First, however, we will address the issue of providing a computational model for expressions that involve assignment and explore the uses of objects with local state in designing simulations. So they're talking about one that we're going to first start by looking at objects. with local state, but also just noting that this situation of imperative programming making it hard to reason about your programs gets even worse when we start to do concurrent programming or parallel programming. And yes, this is 100% true. And with that, we will jump into the second last exercise of this video, exercise 3.7, which states, consider the bank account objects created by make account with the password modification described in exercise 3.3. Suppose that our banking system requires the ability to make joint accounts. Define a procedure make joint that accomplishes this. Make joint should take 3 arguments. The first is a password protected account. The second argument must match the password with which the account was defined in order for the make joint operation to proceed. And the third argument is the new password. So I'm not going to solve this question exactly as it asks. I'm just going to hop into the solution, and I will highlight once again. So this is the full solution, but I'll highlight what I've changed from exercise 3.3. So the first thing you'll note is that I've added an extra internal procedure. So we used to have withdraw, deposit, and dispatch, and we still have them, but now we have the additional make joint, which takes a joint password and returns dispatch, similar to what our outer procedure does as well. The second change we have to make is that we've inserted a lambda into our dispatch procedure. And sort of moved the original parameters. So the original parameters of dispatch were the input password and the message. But now we've lowered that into our lambda because we need to sort of bind to our scope of our dispatch procedure the account password that's going to be linked to the account. So for the joint account, we want to pass in the joint password for the account password. But for the original account, we just want to pass in the original password. So once we've done that, then inside our lambda, we can do everything we were doing before, and we just need to add an extra clause to our conditional expression, which is checking if our message is equal to make joint, and if so, that is going to return us the make joint procedure. And once we've done that, we're done. And we can see that we still have the 3 unit tests from before, checking that we can do our withdraw procedures and our deposit procedures, and we get incorrect password if it fails. But now we also have, we can define account 2 based off of the original account. So we're passing it the original account, and we need the original password in order to invoke the first message make joint. And then we need to provide to this procedure a new password, which is, in this case, can I join? So once we've done this, we now have our account 2 successfully set up. And when we want to do procedures with account 2, we can do it the same way as we did with account 1. And sure enough, the second account holder is just going to withdraw all of the existing funds and set the balance to 0. So once again, similar to exercise 3.3 and 3.4, there's a lot of code on the screen, but the number of modifications that we need to make in order to answer this question is quite small. And last but not least, our final exercise of chapter 3.1, exercise 3.8, which reads, when we defined the evaluation model in section 1.1.3, we said that the first step in evaluating an expression is to evaluate its subexpressions, but we never specified the order in which these subexpressions should be evaluated, example left to right or right to left. When we introduce assignment, the order in which the arguments to a procedure are evaluated can make a difference to the result. Define a simple procedure f such that evaluating plus f0, f1 will return 0 if the arguments to plus are evaluated from left to right, but will return 1 if the arguments are evaluated from right to left. So I'm interested to see what other people come up for their solutions, but I sort of was a bit tricky with my solution. I modified the integers to floating point numbers. But this is my solution. So I've got global index I, and then a global list of values vals, which is just -half and +half. And if we define f to basically set our index to be the sort of running sum of our indices, and then we use that index to do a lookup into our values, we should get the behavior that the question is asking for. So if we're evaluating them, so if the question originally reads 0 and 1. So if we assume that the default is to go from left to right, here we're going to start with an index of 0 and look up index 0 from here. So we're going to be adding -half, and then our existing I is going to be 0. When we add 1 to that, we're going to get 1. So we're going to look up +half, and when we add those together, you'll get 0. If we set I back to 0 and then repeat,
If we do the opposite, our index will first be set to 1, so we'll get half, and the second time when we add 0 to 1, the index will still be 1, so we'll get another half, and then we'll end up with 1. This probably defeats the entire point of the question and what they're trying to get at, but it does sort of work, so that's my solution. But interested on Monday in a couple days to see other people's solutions. If you're free and you want to join, link down in the description to the meetup link. We'll be meeting at 8 p.m. Eastern Time this Monday, as usual. And with that, this brings us to sort of the last thing that I talk about in these videos, which is highlights from the lectures. I believe there's only one small highlight, which isn't really technically related, but up until now, I've sort of been randomly, from the way the chapters have been sort of unfolding, assigning a lecture per week. But I noticed just now, this is like 10 lectures into it, that each of them actually says on one of their title screens which section in the textbook the lectures relate to. So this video that I assigned this week was actually for both sections 3.1 and 3.2. So going forward, I will more accurately be posting the corresponding MIT lecture. That's all I have to say from the MIT lecture. But from the Berkeley lectures, there was this really interesting comment. So I ended up watching 4 Berkeley lectures this week. The first 3 were on object orientation, or the object-oriented programming model, which didn't specifically link to anything in the book. But during one of them, there was a video from Dave Ingalls talking about small talk. And at the very end, the professor, Brian Harvey, made all these comments about C++, Java, the sort of object-oriented language and scheme that they were using, Smalltalk, JavaScript, and Ruby, and then he had sort of this grid. So I have made this grid look beautiful, and I just thought I'd highlight it because I thought it was really cool. So the 3 things that they're looking at, does the language have closures, does the language have uniform reference, and does the language have garbage collection? So interestingly, at the time this was shot, which I believe was in 2010 or when the course was being given, C++ did not have closures or lambdas, neither did Java. But now, as of C++ 11, which came out in 2011, and Java 8, which came out in 2014, both of these languages have support for lambdas. The reason it said kind of before is because I believe Java, I'm not a Java expert, but they have these things called anonymous classes, which sort of operate like closures, but not really. They both now, since Java 8 and C++ 11, have lambdas. So yeah, I just thought this table was kind of cool. It's interesting that these criteria are what I believe Brian and David Ingalls were talking about are what makes an object-oriented language. So interesting that they think that in order for a language to be object-oriented, it needs to have garbage collection. I don't really think that's true, but I guess everyone's entitled to different opinions. And Dave Ingalls was one of the implementers of Smalltalk, so they were the ones that pioneered the idea of object-oriented programming languages. So I guess if anyone is going to have a correct opinion, it's them. But yeah, interesting table to look at. Hope you find this interesting. I definitely did. And that brings us to the end of this pre-recording. So I think this was a bit of a longer one. Hope you enjoyed it and hope you learned something. I'm definitely enjoying Chapter 3 so far, and I'm looking forward to the rest of the chapters. So hope to see you in the next video. Have a great day.